did last time. We kind of fall SDs of this form, which are linear. So, EXT of E XT X of T plus A of T dt and of T X of T plus P2 of T dWt. Okay, so it's and subject to some initial condition x naught. X of 0 is x naught, but x naught is some fixed random variable. So what does this is? This is really a linear SDE with linear drift and linear diffusion actually. And we thought that how to construct the solutions of it and what would be the expectations and the variance of it actually. Okay. The next part that I would like to talk about, I'll not get into the details, all tiny details of the things that I'm going to present now. So you have to read it for yourself from these notes from the Peter Kluder that I gave you last time. I have uploaded them also on LMS. So this is what that you have to do for yourself. I'll just give you a kind of a brief sketch of a new class of SDEs, or those SDEs which are not linear, but they are reducible to the linear SDEs. So reducible to linear SDEs. They are not linear, but they are reducible to the linear. As I said, I'm not going to get into the all technical details of it. I'll just mention the results, so you have to read it for yourself. And I'll just talk about some of examples related with this, and then the different kind of SDEs that you can have, either in linear form or in the non-linear forms. But those non-linear SDEs which can be reduced to the linear SDEs. So imagine I have a non-linear SDE of this form. T x of t, where the drift depends on time, and x of t dt, okay, while f t x of t dw of t. In other words, where the drift and diffusion are these functions, and these functions are, one of these functions could be a non-linear function. The question is how to solve such kind of SDEs. Not all such kind of SDEs can be solved, but there are specific kind of SDEs that can be dealt. So one of the sufficient condition that you can take such kind of a non-linear SDE and turn it into a linear SDE is this actually. So in the book, the derivation of this sufficient condition is given actually. Okay? So the sufficient condition to reduce this to reduce, in other words, to whether we can reduce a nonlinear SDE into a linear SDE. We can reduce this star to a linear SDE of, say, form following, okay, and maybe that form could be dxt, where alpha of t dt plus beta of t dw of t, where this alpha and beta are, some purely functions of time. Okay, so in other words, you can turn it into such kind of SDE if following condition is satisfied. That condition is that I'm going to give you in a second a function gamma. Okay, and that function gamma. This function gamma with respect to the space variable has a derivative 0. So where gamma of ty is this function. So what is this function? It is that function. 1 over pty of the partial b by partial y, and this b is same as this b actually. Okay, the diffusion. Okay, nonlinear SDE minus d of ty times partial or partial y of a ty over bty minus 1/2 partial of bty by partial y. So that's a function gamma of y. So what does this conclusion shows is that if you have been given an SD with some drift and diffusion, and through the drift and diffusion you construct this function gamma, okay, and if the partial derivative of this gamma with respect to y is 0, then you can reduce such kind of a nonlinear SDE into a linear SDE. Okay. Now the detailed treatment that why this sufficient condition is really a sufficient condition is given in the book actually. So you have to read it for yourself. So I'm just discussing this. Okay. So where this function is coming from and why this must be true. So the details are from the book. This is really a lengthy discussion actually. So I don't want to spend time on it. So you have to read it for yourself. And the solution of this star problem. Okay, so what will be the solution of it? Okay, so the derivation of the solution is also given there. Okay, so this condition tells you that whether or not you can reduce nonlinear SD into SD, and then once you reduce the nonlinear SD into this linear SD, then we know how to solve it actually. Okay, and the solution that you're gonna get as a by solving this SDE in the terms of the original coefficients, because here you have these dummy coefficients alpha and beta, which are functions in the terms of A's and B's actually. Okay, so I'll write the solution in the terms of original function. The solution of such a problem can be given as this, so the x of dy, okay, or maybe u of ty, and you can replace y by x of t, okay, so the y is really the dummy variable for x of t, so the u of ty can be computed as the arbitrary constant e to the integral of 0 to t gamma s y ds times the integral from 0 to y of 1 over b of dz and dz. Okay, so this is going to be the solution of this nonlinear SDE. Is it making sense? So, So in order to compute the solution, so what you need? So you need gamma, so you know the gamma, okay? So the gamma can be computed through the B, and you need B itself actually. So if you compute these two factors, this would be the real solution of your first SDE, okay? And in that, when you are trying to write an explicit solution, imagine that you computed this, just replace your y by xt. And that would be really a function of xt that satisfies your given stochastic differential equation. And how you can verify that this function that you have opted is really satisfies the stochastic differential equation, just apply the e to lemma. Okay, so you'll apply the e to lemma, and then you will see that it satisfies the stochastic differential equation. Okay? So I'm just presenting the result. So this is just a result. So you have to see the details, the tiny details from the book for yourself actually. So it's not difficult, it's just very straightforward kind of argumentation actually. Alright. Here is a slight variation of this problem. So imagine, let's take the same problem, but this time, assume that this drift and diffusion are just autonomous function actually. In other words, you have this autonomous differential equation actually. In other words, which doesn't explicitly depends on time, but depends only on xt actually. So it could be just a slight case of it actually, if you remember. But I'd like to just, it's worth mentioning, so I'm just mentioning it for a bit. So a slight variation of this PDE is like that. So imagine you have this dxt as a of xt dt, okay, where this function a, the function a is only a function of xt, and d of xt and dw. Okay, so imagine that I have something like this that I would like to solve. Okay, and where a and b are still nonlinear actually. Okay, a and b are still nonlinear. So what you need to do, the first thing would be that, okay, what would be the now sufficient condition to say that this can be reduced to a linear SDE? And then, once you know that, the sufficient condition, then you're going to ask the question that, okay, what would be the generic solution of this form for such kind of linear SDE? So I'm just mentioning those, okay, without getting into the details, so you have to read it for yourself. All right, the sufficient condition for imagine you are in assumptions to change this, SDE into, say, a linear SDE, okay, of this form, a1 xt plus a2 plus b1 xt plus b2 and dwt. Okay, so like this is the reality and this is my wish actually. Okay, this is my wish. Yes, I would like to turn this SDE into this SDE. The question is, you need to apply some transformation. Okay, the question is, what conditions that transformation should satisfy, and how can I find that transformation actually? Okay, so here's the thing. So the sufficient condition So one thing is pretty much clear. For most of the SDEs, like in deterministic cases, like in the differential equations, nonlinear differential equations and nonlinear PDEs actually, you don't have exact solutions. So you have to do mnemonics. So you have the same cases, same case here actually. Okay. But some exceptional cases of linear ODEs and linear PDEs, you can construct solution, and some exceptional cases of, for example, nonlinear equations, yes, you can also find an exact solution, but those are really exceptional actually. So you have the same case here. So you are really considering and dealing with exceptional cases actually. these are the exceptional cases when you can turn a nonlinear SD into a linear SD and solve it. Okay? These tricks will not work always, but they are good actually. In most of the models, for example, in finance and many different places, can be dealt with this theory. I mean, if there is nothing, then you have always numerics. Okay? So the sufficient condition for turning this SD into this SDE is this, that it should satisfy this B1 partial A by A by dy, where A is some function of y, so I'm going to write in a moment B by dy into B times of dA by dy equal to 0. So this is the sufficient condition, okay, where the A of y is a function that you can directly write that depends on this drift and diffusion, and it goes like this. So A of y over B of y minus 1/2 of the derivative with respect to dy of y. Okay? So in other words, using the a's and b's, calculate your A, and if this A satisfies this condition, you are okay to turn your nonlinear SD into SDE. Okay? And the last thing that I would like to say is that what would be the solution of this SDE? And then I'll go to some examples of it. So what would be the solution of this SDE? Okay. You can. Okay. So the solution of like this SDE, let's call this double star, can be written purely as a function of a space variable. Let's call it u of y. And this is going to be C1. Okay. So there are two cases actually. So if this B1 is not 0, then the solution of the SDE can be written as C exponential e to the B1 times B of y. So I'm going to say in a minute that what it means. And if B1 is 0, okay, then the solution is going to look like as B2 times B of y plus C, where B of y is this time. What is B of y? So the B of y is the integral which starts from y0. In other words, your okay, so if you are writing 0, so it starts from 0 and goes up to y, and ds by dfs. ठीक है? ds by dfs. Alright? So what really I have presented, okay, not a, the rigorous, derivation of all these facts. You have to read it for yourself. The only thing that I have presented is really the results, actually, the facts. Okay, you have to read these for yourself. Okay. So let's talk quickly about this again. So I have a nonlinear SDE, and I want to turn it into this kind of an SDE. Okay. Then the sufficient condition for a nonlinear SDE is to turn a nonlinear SDE into a linear SDE is this actually. Okay. you can have another sufficient condition. I mean, one of the troubles you can say on this is that how can I know B1 actually? Prior to knowing that what would be the linear form of it actually. Okay? I mean, in the book you will see there is another sufficient condition which has been derived from, this equation again, which purely depends on B. So you don't need to borrow anything else from outside actually. And you can know that, okay, if the drift satisfies this condition, drift and the something that depends on drift and diffusion, then you can reduce your SDE into, what do you call, linear SDE. And once you have it, the question is what would be the solution of linear SDE? The solution is going to be depending on that what is the B1 in your reduced SDE actually. Okay, so in other words, and I'm going to say in a moment that when I'm saying that B1 is 0, I really mean that in your SDE you have an additive noise actually. Okay? And if B1 is not 0, that's really going to mean that I have a multiplicative noise. So I'm going to talk in a moment about that, what do you mean by additive and multiplicative noise. So these are interesting two cases actually. So depending on B1 and B1, so you can write the solutions of it actually. Okay? So that's really the basic theory that, which kind of SDEs can be reduced to a linear SDE and how to solve them. Okay? So you have to go through the details for yourself. Let me just do some examples based on it. So it's really rather a tutorial than a lecture. Okay, so let me solve, for example, one equation based on it.